derived principles and experimental methods and so forth to inform demography, so that you can trace it all the way down to molecular level, genetics and so forth, evolution, primatology, sociology, and demography. So there's the context. So that's biodemography. Now, just so everybody's on the same page here with respect to demography, this is really my specialty, is that when we talk about lifespan, this is really a theoretical concept to which at least one member of the species ages. I see my animations aren't working here, and they should come in with that red boxes. But anyway, we'll have to live with this. Okay, so this is a theoretical concept. The record is 122 years. If you ever hear about 140 or 50-year-olds, forget it. This is not. This is not real. You have life expectancy. This is an empirical concept. The average number of years an individual in a cohort is expected to live. This is a metric. This is a statistic. And so for humans, for U.S. men, it's 75 years. For U.S. women, it's 80 years. It's unbelievable, 80 years. Remarkable. At the start of last century, it was 47 and 49 for men and women, respectively. The age-specific mortality, this is one of the most important functions of the life table. And this is the probability that an individual alive this year will die before next year. So for perspective, you have 11-year-olds. This is 1 out of 8,000. These are women. These are female rates. Unbelievable. 11-year-olds don't die. I mean, very, very little. And so this is the lowest probability, or the lowest risk of any place in the life course. And by the way, this is a sort of universal. That is, you go to a developing country versus a developed country, the U.S., Western Europe, and so forth. It's the bottom. The risk is higher in each of these, but the bottom is always right around 10 or 11 years. And then a 50-year-old, maybe 1 out of 350 die before age 51. And then a 100-year-old, it's 1 out of 2. So it's like flipping a coin. Is that the probability of living if you're a centenarian is flip the coin, it's 50%. Flip it again, it's another 50%. So 110-year-olds, just for perspective, is like getting 10 heads in a row as a probability to go from 100 to 110. Oh, this makes me mad. This animation. Well, in any case, we have the age-specific death rate on the left there. So you see this is a schematic. This is schematic. So we have age on the x-axis at the bottom there from 0 to 120. And you have age-specific death rate there on the y-axis. And this is schematic, so you can see here the 1 out of 8,000, so that's the low point. Again, this is schematic, not an actual arithmetic scale. And so you find a little bump here. This is for males, where it's a little higher risk from 18 to 20 right in there. Anyway, then it goes up basically exponentially. And that, so this is 8% a year from about age 30 to 85 or 90 right in there. And then it begins to level off and you get a plateau, although this could be argued whether it's a plateau or not. But certainly it slows at the most advanced aging, or at the most advanced ages. And I have here, it makes me so mad, this isn't working here, but the 92. I have a colleague in Denmark, Kåre Christensen, who talks about 92 is the halfway to 100. Who knows what that means? Okay, I'll tell you. And that is that the same probability of living from 0 to 92, that is, it's the same from 92 to 100. So that gets, 92 is actually pretty old. And but 100, that gives you some sense of how hard it is to get to 100. So those 8 years, the force of mortality in those 8 years is equal to the first 92 years for the force of mortality. So I always use that as kind of a frame of reference. Somebody's in their early 90s, well, okay, that's a marker. You're halfway there. Okay. So what I'm going to walk through here is that the discovery number 1 through, I think I have 13 or so. And so that's how this talk is organized. So number 1, you have mortality slows at the older ages. So I've already shown you that schematic. And I wonder if this is going to,
You're not in presentation mode.
I'm not in presentation mode. Is that my problem?
Right. Is that what you're changing?
Yeah.
Right.
There we go. That's right.
No, yeah, next.
To the right, right there.
That's it.
Oh my God. Okay. So, I thought we were on that. No, I'm not going to go back and show those others. Okay. But look. Okay. Good. So when we first got into this is the late 80s. There was a workshop at Berkeley I was invited to. It's Upper Limit of Human Lifespan. And the conventional wisdom then was that mortality, that is age-specific mortality is an ever-increasing probability of death. So eventually you'll hit a wall of death, which some people can reach no matter exercise, bran muffins, the whole bit. But you can't live beyond. And so in other words, it would be implied that there's a wall of death. So that anyway, here it is. James Fries published in the New England Journal of Medicine, the length of life is fixed. This is 1980. Okay, this implies that, in fact, there's a time bomb out there someplace that you can just live to it, and then everybody would die immediately. Okay, so that would be the mortality wall of death. That's what that implies. So that's age-specific mortality there, and the idea that you attain that, whatever that hypothetical age is out there, that everybody would then, probability of dying in 1 year would be 1. And so that's the hypothesis that we tested. So I'm in entomology. Thank you, entomologists, for showing up here, my friends here. And but I was working with the medfly. This is an invasive pest in California. And I had colleagues, in fact, a student who was working in Mexico at these big rearing facilities. Do I have a picture of that? There it is. So that was the medfly. It's not Drosophila, as in these vinegar flies, but that they use in genetics and so forth. This is a different group. It's about the size of a housefly. So that we go to Tapachula, and then right on the Guatemalan border, and they have basically the General Motors of medfly production. This is 5 tons of medflies a week. I mean, it's just massive numbers. And so anyway, when you get into demography, we're talking about numbers here. So that when you ask questions about what is happening to the trajectory of mortality at the advanced ages, if you have 30 mice or 100 flies and 90% are dead, you have 3 mice or 10 flies. This is nothing. That's the question you want to ask out there. We call it the Hubble telescope of the actuarial world. If you have 1 million flies, then when 90% are dead, you have 100,000. These are big numbers. And so that then you can, get this carries weight for making statements about the trajectory of mortality. Yeah, 5 tons of flies a week. Okay. So we published in 1992, we did this study where we used 1.2 million medflies to measure this. To study the trajectory at the oldest ages. So this came out. And so what we have, 1.2 million, and what we found is that here is death rate right in here. So this is age-specific mortality, the probability of dying. Given that you're alive today, what's the probability of dying before tomorrow? And you have age down here. Here's the citation. And so that if you had small numbers, this is what it would look like. And that is that we take it to, 50 days. If you just extrapolated there, you say, well, of course, it's just continuing to unity and we don't have to study any further. But when you have 1.2 million, you still have 30 or 40,000 out here. And now you can measure the most advanced ages. And you can see here that, in fact, it's slowing. In fact, it decreased. That's the most important aspect of this is less about the details here, that it's a departure from this, what they call a Gompertz. It's a Gompertz model, exponential model, or exponential trajectory of mortality change with age. So that anyway, so this came out in Science. It was, we published in Science, but they had overturning received wisdom and so forth. So it really got a lot of attention and put us on the map. And so anyway, the bottom line was that there's not an upper limit to lifespan. Now, so I had friends on the soccer field. The father came up, one thought, oh, can I cancel my life insurance now? Well, no. But no upper limit is different than infinity. It's not saying you live to infinity. It says that simply that you can't point and say, eureka, I found that age and it is X, and that's the age which medflies or humans or whatever cannot live beyond. Okay, so that's the general carry away concept. Okay, discovery number 2. Females do not always live longer than males, so that women all over the world live longer than males. So this is and so the question is this a general property of all animals? Females live longer. And what we found, well, I'll show you what we found, and that is that here's the gap, and that is this is for humans, 1930 through 2010, female to male gap. So that back in 1930, women lived 4 years longer than men. In the 70s, 80s, right in there, it's about 7 or 8 years longer than men. That's for U.S. And now it's decreasing, so the gap's decreasing back to about 5 years. So is this just unique to humans or in a few other animals, or is there some general property here of all animals, including insects and flies in this case? So here's what we found. And that is we have age-specific mortality here, age right in here, and again, this is age-specific mortality. So it's a probability, given that you're alive today, you're going to die before tomorrow. So you see here that the black line, this is a diet. Okay, we have full diet, we call it. And so the trajectory of males looks like this. Is higher than females, so they're dying off at a faster rate than females. And then it levels off like this, and then the females continue. So it's not so straightforward there. Now, we switch diets so that we have sugar only, and so that now we have females higher than males, but you get the crossover right in here. You get the idea. And now we sterilize them, put them on full diet. Now we get another pattern, so that the males are higher than the females. But each one of these is context specific. So it depends on the, in this case, the diet that you're rearing them on. So that you make these general conclusions that are specifics. It's impossible to predict the sign and magnitude of the sex mortality differential in medflies. The general concept here is that the mortality response in males and females will always differ in identical environments. So look, I mean, humans, behavior is different in males and females, subtle differences. There's physiological difference and so forth. Why would that translate to identical risk? It does not. Is that each one of those factors is going to change the risk in particular ways, and so that the general concept here, because I don't have it, would be that it's context specific for which sex lives longer, if that's a general carry-away message. Okay? Now, discovery number 3. Future therapy. Young replacement ovaries can rejuvenate older females. So I don't just work with insects, I work with mice as well. And I mean, we had extra funds, however that, so I hooked up with the chair of the animal science out at Davis, and he had a graduate student who had transplanted ovaries in a transgenic context of mice. And I believed for a very long time, Ian Gerontology knows this, and others here in ecology and evolution, there's a concept of cost of reproduction. Reproduce early, die young, reproduce later, die later, and so forth. That there's something very fundamental about reproduction and longevity, and so that we talked to them and said, why don't we? Or I said, I'd like to put young ovaries into old mice, and let's see what happens. See what I have here. Yeah. Now let me put this into context, and that is. Last century, early last century, they called it the gland grafters. There's a chapter in the book on this gland grafters. And some guy over in France was getting into transplanting like monkey gonads into humans. Okay, this is crazy science. Anyway, so this didn't work. It was sort of a placebo effect, if there was anything. And so that my feeling is that nobody'd done this before, because it's like, let's stay 100 miles away from this kind of research. It is just kind of crank science, transplanting ovaries or gonads or whatever. And so here's sort of background here. I have, so I pulled this off of, you do a search on newspapers and Google and so forth. Yeah, there it is. Anyway, America's first in-gland grafting, okay? What do I have here? Okay, was the first in the world to record the results of such a procedure. So, what do we have? Yeah, development of senility can be retarded and longevity increased by hormones administered by gland implantation. So this is from the primates, right? And so that, anyway, then what do we have here? Come on, there we go. Okay, many of my patients express a fear that with monkey glands grafted into their own, their lives will likely become influenced by animal instincts. This is most preposterous absurdity. Okay, well, maybe not. There's a movie on that. So okay, I don't know if you saw this. It was absolutely hilarious. Anyway, and then if you want to go to the Kiwanis Club meeting afterwards, you could go there. But look, here's I don't know if you know this or not, but there's a monkey gland. This is on Rachel Maddow and Jimmy Fallon. They were on there. They do this sort